So we've talked about triangles a good amount this year, but in Chapter 6 we're going to start to talk about other polygons, and in 6.1 we start that with polygon angle sum theorems. So first off, we're going to make a conjecture about the relationship between the number of sides of a polygon and the number of triangles we form by diagonals from one vertex. I drew some examples up at that first part. So in the first triangle, I can't draw any diagonals. I can only go to the other two vertices. With my quadrilateral, I can draw one diagonal going from a corner down to the opposite corner. When I start using a five-sided figure, so we'll call that a pentagon. If I start, again, it doesn't have to be at this vertex, but any corner, I can make two diagonals, and it looks like three triangles are formed from that. And if I do the same method with a hexagon, if I draw the three diagonals possible from one vertex, looks like I'm going to make four triangles. So we already know that there's 180 degrees in a triangle. We're going to use this rule to figure out how many degrees are inside my other figure. So we're using the figures up above to fill out this chart, and according to the number of sides, again, triangle has 3, quadrilateral has 4, pentagon 5, hexagon 6. Those figures are in the chart, but we can imagine if I extend that to a 20-sided figure, I would have a 20-sided polygon. Or in general, if I just use n, I could use that for any number of sides. And if I look back again at that shape, it looks like when I have one triangle, obviously I can only make one triangle with a triangle. If I split that quadrilateral in half, that formed two triangles. I have one right here and one right there, so that's upper right, lower left. And I had 3 triangles when I made my pentagon and 4 triangles when I separated my hexagon. So if I notice a pattern, it looks like I can always subtract 2 from the number of sides. That's going to tell me how many triangles are inside that shape. 3 minus 2 is 1, 4 minus 2 is 2, so on. And if I extend that to my 20-sided figure, we don't have to draw it. We just know that if I take 20 sides and subtract 2, I'd be left with 18 triangles. And in general, that's if I start with n sides, n minus 2 would be the number of triangles I would have in my shape. And again, starting from the fact that a triangle has 180 degrees, if I know that there's going to be 2 triangles that I broke up my quadrilateral into, 2 times 180 for 2 triangles is 360 degrees. That's how many degrees I'll see in a quadrilateral. Same kind of concept for a pentagon. Since I can break that up into 3 triangles, 3 times 180, that would make 540. 4 times 180, to have 4 triangles in a hexagon, so that's 720 degrees. If I extend that all the way to an 18-sided shape, that's 18 triangles for a total of 3,240 interior degrees for those angles. And the important rule that we're building here is that if I use n minus 2, so just any number of sides in general, again, I'm always just taking n minus 2, multiplying that times 180, because each triangle has 180 degrees. That's going to tell me how many degrees are inside my figure. So in general, we're also going to have to be able to name our polygons. So we have a few of those up there already. Quadrilateral is 4, pentagon is 5, hexagon is 6. Starting at 7 sides, we call that a heptagon. 8, probably seen before on a stop sign, we call that an octagon. 9-sided figure would be a nonagon. 10, decagon. 11, we don't usually use the word hendecagon, but that is the description. You could always just say, notice how for n we have just an n-gon. Also, except if we say 11-gon, I'll know what you're talking about for an 11-sided shape. 12, there is a name for a 12-sided shape called a dodecagon. Might see that term used in your notes though, instead of just saying 12-gon. So on the next page we have the polygon angle sum theorem, and again this is what we're building towards with our last chart. Whenever I take the sum of the measures of the interior angles of any n-gon, so any kind of polygon, I always take the number of sides and subtract 2, then I take that total and I multiply times 180. That'll tell me how many interior degrees are inside my figure. So if I was trying that with a heptagon, for example, in that first practice problem, all I have to do is realize that a heptagon has 7 sides. So if I take 7 and subtract 2, that would be 5. 5 times 180 means there's 900 degrees total in that figure. Same thing if it was a 17-gon. Notice that we don't have to name it. We just have to list 17-gon as a 17-sided figure. I still do the same work. I subtract 2 from the number of sides. So 15 times those triangles, 180, gives us 2,700 for the total angle sum on the interior. You can also use that rule and go backwards. I know that if the interior sum is 1,980, the equation that I could set up to find the number of sides is use that same formula. I know that n minus 2 times 180 will give me my total. This time I know the total, I just have to figure out what n was to begin with. So we're just going to work our way backwards. We can use our algebra steps. If I'm multiplying by 180, I can get rid of that by dividing. And then if I have n minus 2 and I have 11 after that division problem, I get 13 for the number of sides. So you can use that rule forwards or backwards. I can take 13, subtract 2, and then figure out how many degrees I have in my figure. Or I can start with the degrees in the figure and work my way back to get that there were 13 sides. So also a few other terms that we'll need to know too in this section. Equilateral polygon means that we have a polygon with all sides congruent. Again, equa, you just want to think equal, and lateral referring to sides. Similar in our next description, if I say equiangular, it's a polygon with all the angles congruent. So very close, but again, equiangular just means equal angles. And regular polygon is when we have both. So a polygon that is both equilateral and equiangular. If we notice that drawing, it looks like all sides are congruent and also all angles are congruent. So when you use the regular polygon, that's what we're referring to. And if I follow with a corollary, so last time we're looking at the total degrees in our figure, now I can look at the measure of each interior angle, so not everything put together, but just one angle at a time. The only thing we have to do is we have to take that angle sum from before, and again, that's the same formula, n minus 2 times 180, but now I just have to divide it by n to find out what each angle is. So if I'm trying that in the practice problem number 2, to find out the measure of each interior angle in a regular hexagon, notice that it does have to be a regular hexagon. If it's irregular, we don't know that they're all even, but if I know that it's regular and a hexagon has 6 sides, I know that I can follow my formula. If I take 6 minus 2 times 180, that'll tell us first of all that there's 720 degrees in that figure, and if I divide that evenly into 6 angles, it tells me that each angle will be 120 degrees. Trying that same process with a nonagon, only thing that's different is now I have 9 sides instead of 6, so I follow the same formula for the top. 9 minus 2 would be 7, so if I multiply that times 180, I know that there's 1,260 degrees in the figure in total, and if I divide that evenly into 9 angles, I know each one will be 140. So again, same thing that we found from before, we do that work for the top. Got to figure out how many total degrees are in that shape, and if I break that evenly into the number of sides, that tells me what each angle will end up being. So we can also work our way backwards to figure out what the measure of an angle is if I start with the other angles in that figure. So if I start with a pentagon, and that pentagon today, I can first figure out how many degrees should be in that shape to begin with. And we know how many degrees should be in our pentagon because we're just following our formula. N minus 2 times 180 should tell us that there's 540 degrees in any pentagon. Again, this is not a regular pentagon because the sides and angles are not congruent, but any pentagon should still have 540 degrees on the inside of that shape. So if I know that the entire shape should add up to 540 degrees, just like with our triangles, I just got to take 540 and subtract all the angles that I already know. So off to the side, I was just doing that work. 540, subtracting 110, subtract 90, subtract 120, subtract 150. That should tell you that there's 70 degrees left for that last angle, and that was angle Y. Same work if we're doing a quadrilateral. Only thing that's different is now I'm going to have a different sum for my angles. If I take 4 minus 2, multiply that times 180, you might remember from our first chart that we had 360 degrees every time we're making a quadrilateral. And it doesn't have to be a regular quadrilateral. Again, could just be any sort of shape with 4 sides. I know that any 4-sided figure should have 360 degrees on the inside. So same as the last question, take 360, subtract the 3 angles that you're given, and that should tell you what's left. And I believe that should be 102 degrees for that last angle. So we've been working at interior, but we can draw what we call exterior angles at any vertex of a polygon. These 2 figures below show that the sum of the measures of the exterior angles with 1 taken at each vertex. So for example, I have 1 at this vertex, that would be an exterior angle of 150. Another exterior angle is 80 degrees, and this third exterior angle is 130. If I add those 3 exterior angles together, I'll get 360 degrees. So that was a triangle in our first example, but I have a quadrilateral in the next one. Taking those exterior angles, now I should just have 4 of them. 75 plus 115 plus 71 plus 99. All those exterior angles should still get us 360. You can imagine that's the case because if I take those exterior angles and basically put them all right next to each other, that's going to form a circle around my shape. And we should know that circles are always going to make 360. So we're going to throw another rule on top, and again, this is looking at exterior angles. Just like what we said before, the sum of the measures of exterior angles in a polygon, so again, you want to think outside for exterior, they should all add up to 360. And again, doesn't matter what shape, we saw above with a triangle and a quadrilateral, it's still the same measurement. Every time we have exterior angles, they should always add up to 360. So for a pentagon, it would be the same idea. If I find all of these angles, 1, 2, 3, 4, and 5, they should all add up to 360. And then we're going to use that on the bottom of our practice here to find the measure of one exterior angle. We know that the measure of all the exterior angles, again, should always be 360, so that's not really going to be a question. But if I need to find the measure of one angle in an octagon, I can take that total, and again, I don't have to do any work to find the total. I just know that the exterior angles should add up to 360. I can take that sum of the exterior angles, divide it into 8 angles, because we're using our octagon. That gives us 45 degrees for each angle. One thing that is missing in this question is it would have to be a regular octagon. So it would have to be kind of like this is a regular pentagon. All the angles should be the same. So these should be regular figures. You might look at an example like these two up above with your triangle and quadrilateral. If it's not a regular figure, so if I have different angle measurements, I'm going to have different measurements also for the exterior angles. So just with that in mind, these two rules at the bottom only work if it's a regular figure. So for an octagon, I divide that 360 evenly into 8 angles. That gives me 45 for an exterior angle measure. Same work if it's a nonagon, but the only difference is now I'm taking that exterior angle sum. I take that 360 degrees. Now I'm just dividing it into 9 equal angles. And 360 divided by 9 will give us 40 degrees. So we've looked at rules for exterior and interior angles of our polygons, and we'll be practicing that in class.